Good morning, students. Myself, Dr. Shantani Bhattacharya, Assistant Professor of EC Department, SRM Institute of Science and Technology, Kattankulattur, Chennai. Today, I am going to start new chapter. It's called Digital Logic Gates. Okay. So, starting with what is digital logic gate? Digital logic gate is an electronic circuit that makes logical decision based on the combination of digital signal present on its input. Okay, so here there are so many a number of inputs are large. Okay, that means more than one inputs. Okay, but the output will be only one. Okay, and the logic network is actually the collection of logic gates interconnected in such a way that it behaves as a switching functions. Okay, like on off, high low, true false, like that. So which logic gates today will cover? This is actually AND gate, OR gate, NOT gate, NAND gate, NOR gate, and XOR gate, and also XNOR gate. Okay, so starting with AND gate. Okay, so I hope this lecture will go very interesting and it is very scoring. So if you understand, listen to me properly. I think hope all of you understand properly. So what is AND gate? AND gate is actually this is actually the symbolic diagram of the AND gate. You can see. So here there are two inputs, A and B, and X is actually represented as output. Basically, here output it is represented as A dot B or AB. You can write A dot B, or you just omit the dot term. It is you can write as a AB. This is actually AND function is actually a multiplication process. Okay, now I am coming to the truth table. So here there is a input A, input B, and output, that means it is denoted as X. Okay, so we will take 4 combination like 0 0 0 1 1 0 1 1 combination. So this is actually just a multiplication, nothing but multiplication. So if you multiply 0 and 0, say this will come 0. If you multiply 1 and 0, this will also come 0. If you multiply 0 and 1, so it will again come 0. So only if both the inputs are 1 and 1, then only the output will come 1. That means multiplication will come, result will come 1. So you can say in other way that when both the inputs are 1, then only the output here gives 1. That means the question may comes like that. Give the name of the gate where when the both the inputs are 1, then only output gives. This is one type of question. This type of question may come. Then this is the answer is AND gate. Okay. Now coming to the next OR gate. Okay, so OR gate, this is actually the symbolic representation of the OR gate. Here A and B is the input and X is the output, similar as AND gate, but just see the difference. This is actually the symbolic representation. Now now I'm coming to the truth table. So here A is input, B is input, and output is represented as X. It is actually denoted as A plus B. That means it is the addition. Okay. So now again same combination we will take 0 0 0 1 1 0 1 1. So just if I add 0 plus 0, so it will come 0. So 0 plus 1 1, 0 plus 1 1. Then 1 plus 1, again it will come 1. So here you can see, you can say in this way that here only when both the inputs are low, then only the output will give the low. Otherwise in each and every case output will be high. So this is actually the OR gate. Okay. Now coming to the inverter or NOT gate. The NOT gate, basically usually we use the term NOT gate. It is actually the inverter. Inverter means this is actually the symbolic representation of the inverter. Input is A and output is A bar. There is a one this type of not symbol. This is actually the not symbol. So it is actually the complement of the input. So a and a bar. Bar is actually represented as complemented form. That means if there is a already here truth table is given input and output, so if there is 0 is input, then our complement form is just inversion form. That means 0, if 0 is input, output will be 1, if 1 is input, output will be 0. So this is the NOT gate. Okay, now coming to the switching circuit of the gate operation. So here actually the basic structure of the AND gate, it is in the starting slide I have already said that all are behaving as a switching circuit. So AND gate is actually behaves like a series circuit. Okay, so it is series switching circuit, but OR gate it acts as a parallel gate. Okay, and this is a representation of the NOT gate. Now coming to the NAND gate. NAND gate is actually, this is the representation of the symbolic representation of the NAND gate. A and B is the input, X is the output. So here basically X is actually A dot B bar, or you can write AB bar. That means whatever the AND gate will come, just its opposite is actually the NAND gate. Okay, that means you can say AND plus NOT is actually a NAND gate. Okay, so now I am just opening a one node which I think if I explain it, then it will be helpful for you. So now I am representing NAND gate. Okay, so this is actually the NAND gate. Here A and B is the input, and we just considered here X is the output. It is represented as AB bar. So now what will happen actually, if I take a truth table A, this is B. Okay, so now first we will calculate AB, that this is actually the AND operation. Okay, then we will calculate AB bar. So now I will take 0 0 0 1 1 0 and 1 1 combination. This 4 combination we will take basically everywhere. Okay, so in the case of, first of all, in the AND operation, 0 0 means 0, 0 1 means 0, 1 0 means 0, 1 1 means 1. So just in the complement, that means this bar is represented as complement form. I have already said all this bar related information in the my previous lecture. If you didn't follow my previous lectures, you just go and you can understand easily. So just opposite. So if there is a 0, bar is 1. So if there is a 0, so bar is 1. So here also 0 1 and 1 0. That means, so now AND gate operation, so A, B, and answer is this one. Okay, so A, B bar. Okay, just opposite the, here we can represent it in such a way, that means this is the AND gate, and after that this is a NOT gate. That means A, B, so this is A, B, and output will come AB bar. We can represent it in such a way. That means here only, when only both the inputs are high, then only output will goes low. This is very important part. Okay, when both the inputs of the NAND gates are high, then only output goes low. Okay, otherwise in any combination output goes high. Okay, now I am again going to my presentation. So this is actually the NAND gate. Okay, now coming to the NOR gate. NOR gate is actually, this is the symbolic representation of the NOR gate, where A and B is the input, X is the output. It is nothing but just it is actually represented in such a way, A plus B bar. So we can say like that, if I first I use a OR gate, and then if I use a NOT gate, then it is represented as NOT gate. That means OR plus NOT, it is actually a NOR gate. Okay, so same thing I will now do for same calculation we will do for here OR gate, NOR gate. Okay, so now I am discussing about NOR gate. Okay, so what is this? Actually NOR gate we will represent it as in this way. Okay, so this is A, this is B, this is X. X we will represent it as A plus B bar. Okay, so you can represent it in such a way also. This is OR means if there is a and B is the input, then output will be A plus B. Okay, and then if I connect a NOT, then it is A plus B bar. Okay, so now I'll take A, B, and then A plus B. Okay, so after that A plus B bar. So combination, same combination, 0 0 0 1 1 0 1 1. Okay, same combination. So these are basically input and these are basically output. Okay, output. This is basically for OR gate, and this is NOR gate output. So now in the what will happen in the OR gate, 0 0 means 0, but otherwise in any other combination it will come 1 1 1. But in the case of NOR, that means just its opposite, that means bar, complemented form. That means 0 it will come 1 1, it will come 0 1, it will come 0 1, it will come 0. So here the important part is very important. When both the inputs are low, at that combination only NOR gate shows the output high. Otherwise in any combination the output goes low. This is very important part. Okay, now coming to the lecture. So this is actually the representation of the NOR gate. Okay, so you can say like that NOT and OR. Okay, so now next is, I have already said that NAND and NOR representation, that means AND plus NOT, it is actually NAND. Just before the AND gate, if I add any NOT gate, then it will be represented as NAND gate. Same as before the OR gate, if I add a NOT gate, then it will, we can represent it as a NOR gate. Okay, now another important term is this, that means NAND gate as bubbled OR gate. Okay, this is also very important part. That means if I use a OR gate and if I add two NOT, this red symbols is basically represented as a NOT. If I represent these two NOT here, then we can represent it as a NAND gate also. If you follow my next lecture, in this lecture I will describe how we will basically use this bubble OR gate. Okay, so what is this? If bubble OR gate, if before the, that means if before the, that means I mean to say if I add here this two NOT gate, then before that means the OR gate, then it will, we can represent it as a NAND gate. Okay, same as if there is a AND gate, this is actually the AND gate representation. If I add two NOT gate here, then we can represent it as a NOR gate. Okay, so how, let's see, this is actually A and B. NOR gate means A and B, and output we all know already, that is A plus B bar. So here what will happen? Here it is, if there is a and there is a B. Okay, so after NOT, I have already said this two bubble is actually represented as NOT. So it will, so input of the AND gate is actually A bar and B bar. So output will come A bar dot B bar. So this is actually A bar dot B bar means actually A plus B bar. So it is actually in the previous lecture I told about the De Morgan's theorem. Please check this video. You can understand this is actually based on De Morgan's theorem. This is actually if a plus b bar means according to De Morgan's theorem it will come a bar dot b bar. So this is actually applying the De Morgan's theorem, this type of bubble gate is produced. Okay, so next video we will share basically how we will use this bubble AND gate or bubble NOT gate or gate. So it is very helpful to all of you. Please keep watching. Okay, so now coming to the exclusive OR gate, this is also very important. So here this is the symbolic representation of the exclusive OR gate. So inputs are A and B, output is X. So here one thing, here input A, input B, output. So here same combination we have to take 0 0 0 1 1 0 1 1. So here we can see that only when both the inputs are different, that means one input is, that means input A is 1, input B is 0, or input A is 0, input B is 1, then only output will goes high. Otherwise in any combination the output goes low. Okay, so this exclusive OR we can represent it as in such a way A B bar plus A bar B. So now just I am quickly again open another slide that this is based on XOR gate. Okay, so XOR gate we represent A B bar plus A bar B. Okay, so how the here actually it already here shows if it is Y, so 0 0 0 1 1 0 1 1. Okay, so here it is showing that only 0 and 0 1 1, that only these two combinations the output will come 1. So just check in this way. First we will take two input. Okay, so then we have how we will basically find out this Y is actually A B bar plus A bar B. Okay, so now first of all we have to find out A bar, then B bar. Okay, then A B bar, then A bar B. We can represent in both ways, in dash form or bar form. Okay, then AB bar plus A bar B. Okay, this is the whole representation. Okay, so now starting with 0 0 0 1 1 0 1 1. Okay, so first of all I just I will find out what is A bar. So it is 1 1 0 0, opposite term. Then B bar is 1 0 1 0. Okay, then we have to find out A bar and B, first of all A B bar. So that means we will take this A B bar, that means 0 and 1 0, this is just an AND operation, 0 1 0. Okay, then 0 and 0, this is 0, then 1 and 1, this will come 1, then 1 and 0, this will come 0. Now A bar B. Okay, so I will take this component and this component. So now 0 and 1, so this is 0, again 1 and 1, this is 1, so 0 and 0, this will 0, then 1 and 1 0, so this will also 0. Now we have to find out, just we have to sum these two components. Okay, these two components, 0 0 0 0 1 1 1 0 1 0 0 0. So just see, we have started AB, these two input, and output will come 0 1 1 0. The same thing here also. This is actually the elaborately I explained all the terms, so how it actually comes, I shows the detailed result. Okay, now I am starting with the next part, this is exclusive NOR gate. Okay, so this is actually the symbolic representation of the exclusive NOR gate. So there is also A and B is the input. This type of one another term is there, this type of shape is there, then output will X. Okay, so now this is actually the exclusive OR is actually complement of the exclusive OR. Okay, so again same combination we have to take 0 0 0 1 1 0 1 1. So here basically output will come 1 0 0 1. Okay, so you can see that here only what will happen, so only when both the inputs are same, we can say in this way, that means here both inputs are same, 0 and 0, 1 and 1. So when both the inputs are same, then only output goes high, otherwise in any combination output goes low, and we represent the output in this way, A bar B bar plus AB. Okay, or A B bar plus A B bar plus A bar B bar. Okay, so we can represent in this way also. So I'm just quickly open it. One another thing I want to say, this A B bar plus A bar B, we can represent it in such a way also. Okay, this is A, actually A XOR B. So now I am going to the next side, that means XNOR. Okay, XNOR, that means it is actually if A and B is the input, then output will be, what will happen, A bar B bar plus AB, that means AB and A bar B bar. Okay, so this is actually the output. Okay, so now what will happen, so if there is a I just show you the this is two input, Y is the output, so this is 0 0 0 1 1 0 1 1. So this is the combination, so it will come 0, it will come 1 1 0 0. So this is in this way, actually here this is A, this is B. So in this way we have to find out 0 0 0 1 1 0 1 1. Same process here also we have to follow. Okay, same this is actually the bar representation, that means this bar representation here. Okay, this bar representation. So if I just multiply this A B, this part, this will come 1 0 0 1. This is actually we can say this is the XNOR combination, that means AB plus A bar B bar. Okay, so this is actually the combination of XNOR. Now I'm just ending my today's lecture. So thank you, keep watching, so it will be very helpful. So all of you, thank you.